Suppose you connect a supercapacitor to a power source, and within a very short time it becomes charged. Now disconnect it, and the device can still deliver electrical energy. But where was that energy stored? Did the electricity enter deep inside the electrolyte, or did it become trapped inside the carbon electrode? Or did it something happen at the boundary where the electrode and electrolyte meet? The answer lies in the region so thin that we can't see directly. It is only a few nanometer wide, and this region is called the electric double layer. And once we understand this layer, the working of electric double layer capacitor becomes much easier to understand. So let us follow the charge from the external circuit to the electrode surface and see exactly where it goes. So when a voltage is applied, electrons move through the external circuit and accumulate on one electrode. The other electrode loses electrons. So one electrode becomes negatively charged while the other becomes positively charged. But the electrolyte between them also contains charged particles. They are so-called ions. And these ions respond immediately to the electrode charge. So near the negatively charged electrode, positively charged ions move towards the surface. Near the positively charged electrode, negatively charged ions move closer, and this creates two neighboring regions of opposite charge. One charge remains on the electrode, the opposite charge is present in the electrolyte, and this separation of charge at the electrode-electrolyte interface is called electric double layer. The important point is that electrons remains inside the electrode, the ions remain inside the electrolyte, and they come very close to each other, but they do not mix. You may imagine two groups standing on the opposite side of thin glass wall. They can come very close, but the wall keeps them separated. This is only a simple analogy, but it captures the central idea. The energy is stored because opposite charges are separated across an extremely small distance. So now let us look more closely at the electrolyte side. The sign of the electrode decides which ion move towards it, and ions having the opposite charge are called counterions, and ions having the same charge are called coions. So when the electrode becomes negatively charged, positive counterions become concentrated near its surface. At the same time, negative coions move away from that region, and the reverse happens at a positively charged electrode. So the double layer formation is not simply the arrival of counterions. It also involves the depletion of coions near the surface. Together, these changes create a local charge compensating layer. Still, the complete electrochemical cell remains electrically neutral. Charge has not been created. It has only been separated and redistributed. This is the key point. A supercapacitor stores charge not by hiding electricity somewhere in the bulk, but by arranging electronic and ionic charges across a very small interface. But how exactly are these ions arranged? Are they packed in one fixed layer, or are they spread gradually into the solution? To answer that, scientists and researchers develop different types of models. The first model is Helmholtz model. Helmholtz imagined the interface as two compact layers of opposite charge. One layer lies on the electrode surface, and the second layer of counterions lies just next to it in the electrolyte. The arrangement looks similar to the conventional capacitor, and this is why the model is often represented using the relation C equals epsilon A divided by D. Here, C is a capacitance, epsilon is the permittivity of medium, and in simple term, it describes how the surrounding medium responds to an electric field. and A is the accessible interfacial area. D is the effective distance between the opposite charges. And this equation tells us two important things. The capacitance increases when more surface area is available. It also increases when the charge separation distance becomes smaller. And the Helmholtz model gives us a very clear physical picture. But there is one problem. Real ions are not fixed like tiles on the floor. They are continuously moving because of their thermal energy. So the idea of one perfectly ridged ion layer is too simple for many real systems. And this limitation lead to the next model. So Gouy and Chapman included the effect of thermal motion. So electrostatic attraction pulls counter ions towards the charged electrode, but the thermal motion tends to spread them through the electrolyte. So these two effects compete with each other, and as a result, the ions do not remain in one fixed plane, but they form a diffuse layer. And the concentration of counter ions is the highest near the electrode surface. And as we move away from the surface, their concentration gradually decreases, and their electrical potential also decreases smoothly with distance. In the electrolyte, the distribution is controlled by electrostatic forces and thermal motion. The Gouy and Chapman model therefore gives a more dynamic picture than the Helmholtz model. It also explains why the diffuse layer becomes thinner when the electrolyte concentration increases. But this model also has limitations. It works best for the dilute electrolytes. It does not fully account for finite ion size, ion crowding, or specific adsorption near the electrode surface. So one model describes a compact layer and the other describes a diffuse cloud. The next question was obvious. Can both ideas be combined? The Stern model combines the Helmholtz and Gouy-Chapman pictures. Very close to the electrode, it includes a compact region, and beyond that compact region, it includes a diffuse layer. So the ions nearest to the electrode are treated differently from the ions further away, and the potential first decrease across the compact region and then it continues to decay through the diffuse region. And this gives a more realistic classical description of electrode-electrolyte interface. The total capacitance can also be understood as a series combination of compact layer and diffuse layer contributions. That means that regions influence the final double layer capacitance. The Stern model is more useful than either earlier model alone, but it is still an idealized continuum model. Real electrodes are not perfectly flat. Their surfaces may be rough, chemically non-uniform, and highly porous. The electrolyte may also behave differently inside a very small pores. So classical models help us to build the understanding, but the real supercapacitor electrode require additional factors to be considered. Now let us place the three models together. The Helmholtz model gives the simplest picture. It assumes that the counter charge forms one compact layer near the electrode, and the potential decreases approximately linearly across that layer. And the Gouy and Chapman model introduces thermal motion. It describes ions as a diffuse clot and the potential as a non-linear decay into the electrolyte. The Stern model combines both. It contains a compact region near the surface and a diffuse region beyond it. So these models are not three completely separated up explanations. They represent a progression in scientific understanding. The Helmholtz model explains simple charge separation. Gouy-Chapman model adds ion motion and distribution. The Stern model brings both ideas together. Still, none of these models alone tells us how much capacitance a real nanoporous electrode will produce. For that, we must look at the electrode structure and the electrolyte together. So, what actually controls double layer capacitance? The first important factor is accessible surface area. So a carbon material may have a very large total surface area, but only the surface that ions can actually reach can form an effective double layer. So the total area and usable area are not always the same. The second factor is ion size. In a liquid electrolyte, ion is usually surrounded by solvent molecules. This surrounding layer is called the solvation cell, and because of this cell, the effective size of the ion can be larger than the bare ion itself. That affects how closely the ion charge can approach electrode. The third factor is pore size and pore accessibility. So nanoporous carbon contains very small pores, and some pores may be easily accessible to the ions, others may be too narrow or poorly connected. If the ions cannot enter a pore, the internal surface of that pore cannot contribute effectively to the charge storage. Electrolyte concentration and dielectric environment also influence ion distribution and charge separation. The situation becomes even more complex in sub-nanometer pores. Inside such narrow spaces, ion packing may change. An ion may also lose part of its solvation cell. This process is called desolvation, and therefore a high surface area alone does not guarantee a high specific capacitance. And the electrode pore structure must match the size and behavior of electrolyte ions. In simple words, the electrode and electrolyte must work as a coordinated system. Now we can connect this entire discussion with the working of an electric double layer capacitor. A porous carbon electrode contains a very large number of internal surfaces. Whenever the electrolyte reaches these surfaces, a double layer can form, and each small interface behaves like a tiny charge storage region. And one such interface stores only a very, or you can say, small amount of charge. But a porous electrode contains countless interfaces. Together, they produce the measurable capacitance of the device. In an ideal EDLC, charge is stored mainly through electrostatic separation. There is no required bulk phase transformation during ideal double layer charging. This helps explain why EDLC can charge and discharge rapidly. But rapid charging does not depend only on the charge storage mechanism. The ions must be able to move through the electrolyte and enter the pore. Electrons must also move sufficiently through the electrode. If pore access is poor or the resistance is high, the practical performance decreases. So the final behavior of EDLC depends on several connected factors. The first one is accessible surface area, pore structure, ion arrangement, electrolyte properties, and electrical resistance. So electric double layer is the foundation, but the entire electrode electrolyte system determines how well the device performs. Let us return to the doubt with which we have started. So where does the electricity hide? In an ideal electric double layer capacitor, it does not hide deep inside the electrolyte or inside the bulk electrode. It is stored at the interface, and electrons remain on the electrode surface. Counterions arrange themselves in the electrolyte near the surface, and opposite charges remain separated by an extremely small distance. Helmholtz described this interface as a compact layer, and Gouy and Chapman explained that thermal motion creates a diffuse ion distribution, and Eastern combined both ideas into a compact region followed by a diffuse region. In a real nanoporous carbon or electrode, the capacitance also depend on the accessible surface area, pore size, ion size, solvation, desolvation, and electrolyte conditions. So the central idea is simple but powerful. Supercapacitor stores energy through the countless nanometer scale interfaces. At every accessible surface, electronic charge and ionic charge come extremely close. They do not cross into each other. They remain separated. And that controlled separation of charge is the electric double layer, the basic foundation of ideal EDLC charge storage.